All right, that was a long discussion just to prove the infinite sum. All right, now that we have that settled, we can look at, well, before we look at the next one, we're going to look at one specific counterexample. And that is, what happens if we misuse the sum to infinity formula? Now, as stated before, this formula only works if r is less than 1. Because otherwise, we're going to get weird things. Let's see what happens if we don't obey this rule. If we ignored this rule. That means, let's say r was equal to 2. Well, that means if we started, let's say a was 1. So that means we would have this progression. 1, 2, 4, 8, 16. Basically, the powers of 2 increasing forever. Suppose we plug this into the formula. A here is 1, and then the ratio here is 2 because every term is multiplied by 2. Well, 1 minus 2 is negative 1. So 1 divided by negative 1 is negative 1. That means that 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus ... is equal to negative 1? Now, obviously, here comes the reason why you should be very careful when you use this formula. If you don't obey this condition, you're going to get some really, really weird and oftentimes contradictory and really concerning results. Right? Like, how does the sum of every power of 2 get to negative 1? Right. Now, obviously, there's going to be some definition in math that says this is true, but only if you apply it to some specific case or only if a certain condition is met. But in general, if we're talking about the most bare bones definition of summing, this right here is nonsense. Okay, there is no way in this system that we're working with where you can sum all the powers of 2 and eventually get to negative 1. That makes no sense, right? So this is divergent. You cannot use the sum to infinity formula because it's a divergent series. This right here is basically what we call the convergence condition, right? So basically, the only time that the sum to infinity of a geometric progression exists is if the series itself, is if the series itself is convergent. Now, let's go to the second part. Actually, you know what? Before we get to the second part, let me talk about the means first, because I think the means will be quicker to explain. So the means of an arithmetic and geometric progression basically just involve the mean of 2 terms. So for example, if I had a plus nd and a plus n minus 1d, so just any 2 consecutive terms in an AP, this is for AP, I want to know what's the mean of these 2 terms. Right? So the mean is essentially just the average. So means basically mean average. So the way to take the mean of this thing is to, we're going to call this AM. So this AM stands for arithmetic mean. And essentially what this means is that we're going to take the average of these 2. So we're going to take A plus ND plus A plus N minus D, and we're going to divide it by 2. All right, so if we sum this, we're going to get 2a plus 2nd minus d over 2. I think that's correct. 2a plus 2nd minus d, which is going to get us, let's see, it's going to give us a plus nd minus d over 2, right? So this is like an arithmetic mean between 2 things. But in general, if we were to look at the arithmetic mean of, let's say, a and b, the arithmetic mean of a and b, 2 numbers a and b, is just going to be the average of these 2. So a plus b over 2. So in general, how we define the arithmetic mean, the definition of an arithmetic mean, is if the arithmetic mean basically states that, let's say A, B, C are in an arithmetic progression, then that means that their arithmetic means are an arithmetic progression. Right? So that means that, let's say B is the arithmetic progression of A and C. That means that C minus B should be equal to B minus A. Right? So this is assuming that B is the arithmetic mean of A and C. All right. So that means that if it's the arithmetic mean, that means that A plus something equals B, and then B plus something equals C. So, but these are increased by a constant, right? The same thing, right? They're increased by the same thing. So A, B, and C are in arithmetic progression. So that means that the difference between B and A must be equal to the difference between C and B because they're in arithmetic progression. If we try and solve this, we get 2B equals to A plus C, and we get that B is equal to A plus C over 2. So that means, in general, for any two numbers A plus B, A and B, the arithmetic mean of A and B is A plus B over 2. Okay? So this is how we define the arithmetic mean of two numbers. Now the geometric mean is a different story. Geometric mean is if these two numbers are in GP, so let's say A and B were in GP. That means that B is going to be some multiple of A. So this K here is our common ratio, as we saw just now in the GP. So that means that A and B are in your GP. So let's let C be the what we call the geometric mean. Geometric mean, or GN, of A and B. So what this means is that these two must be in. This means that ACB must be in geometric progression because it is the geometric mean of A and B. So that means it is the geometric average of A and B. If A and B are in geometric progression and C is the geometric mean, then that means that it is the average of these two in geometric progression. Right? It is the average of A and B in a geometric progression. So that means that by the definition of common ratio, B divided by C, which is going to give us the common ratio, must be the same as C divided by A. Right? Because we are trying to obtain the average of these two in a geometric progression. So that means that if we multiply it by some factor, we're going to get this, and then multiplying this by some factor is going to get us this. Right? So that's the geometric mean of two numbers, is trying to get the average in a geometric progression. Solving this, we're going to get C squared is equal to AB. All right, now assuming that both A and B are positive, we're not going to say that it's negative. So we're just going to say that C is equal to the square root, the positive principal square root of AB. So this right here is the geometric mean of A and B. Right? And if you can see, let's summarize what we just said. The arithmetic mean of A and B is equal to A plus B over 2. And the geometric mean of A and B is equal to square root of AB. Right? Now, there's a very famous result, which I'm not going to prove in this video. You can go look up proofs on your own, or if you want me to make a video on it, I might make a video on it. What's known as the AFGM inequality, the arithmetic mean, geometric mean inequality. This states that for all A and B, which are whole numbers, so positive integers, A plus B over 2, oh sorry, not positive integers, positive rationals, I think. Positive reals, I think. Yeah, positive reals. For all of them which are positive reals, the reason it has to be positive is so that we don't run into negative number problems with this. This is greater than or equal to square root of AB. Right? You can correct me if I'm wrong about this, whether or not it's not just positive reals and negative reals supposed to be included, as long as they are the same sign. Because I think if it's the same sign, it should be no issue. Yeah, if it's the same sign, there shouldn't be a problem. Actually, no, there will be a problem because this is positive, and then if A and B are both negative, there's going to be an issue. Right? You can correct me if I'm wrong the condition on it, but this is generally what people consider to be the AMGM inequality, is that the AM is always going to be either equal to or bigger than the geometric mean. There are lots of ways to prove this. I'm not going to prove it right now. But yeah, you can go look up the proof on your own. But yeah, this is a very important inequality in math, as this can be used to solve a lot of problems. All right, let's cap it off with the last topic of the day, an arithmetico-geometric progression. So what this is basically just the creme de la creme. It's the combination of all of the progressions we have discussed. The arithmetic mean geometric mean the arithmetico-geometric progression, or AGP, is essentially a progression that is both arithmetic and geometric. So we have an arithmetic term multiplied by some ratio. Or in this case, we can even say that it is an arithmetic times some geometric. It's two terms, multiplies the first term. And then it's basically just an arithmetic and geometric progression just sewn together. Right? It's exactly what it looks like. It's just going to be the sum. Sorry, it's just going to be every term is going to be a arithmetic term. As you can see, the arithmetic terms are, we're going to underline the arithmetic terms in blue here. These are the arithmetic terms. And then the geometric terms are the others, which I'm going to highlight in red. So these are the geometric terms. So this is in general what an arithmetico-geometric progression is. It's just an arithmetic and a geometric progression just kind of like brute force sewn together, like multiplied together. All right. So obviously, Tn here is very easy to find out. Tn here is simply a plus n minus 1 d multiplied by b times r to the power of n minus 1. Right? And that is in fact the general formula of a general term for an arithmetico-geometric. S of n, however, is going to be a bit of a challenge. So let's see what we can do. Well, let's take S of n. S of n is going to be equal to summing all of these, like all of them, like this. And so on. So we're going to sum the first n terms, basically, of this arithmetic geometric mean. So we're going to sum all the way up to the nth term. Okay, so what are we going to do? Well, the way to find this is actually we're going to use the same trick that we did with the geometric mean, and we're going to geometric progression, and we're going to multiply it by r. Right? And you're going to see why we're going to do this in a second. This is going to be a plus 2d br cubed plus dot 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 plus a plus minus 1 d br n. And we're going to take the difference of the two. Right? We're going to take equation 1 and equation 2 and subtract them. Right? This subtracted by this is the same, but this one is going to have some difference. We're going to have ab plus a plus d br plus a plus 2d br squared plus dot 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 plus a plus n minus 1 d br n minus 1. And we're going to subtract all of this thing that we just added. So minus a br plus a plus d br squared plus dot 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 plus a plus n minus 1 d br n. Actually, we're gonna add one extra term here. We're gonna turn this into n minus 2 and make this bn minus 1 because that's the original. We just it's supposed to be n minus 2 and n minus 2, but we multiplied by r in this bottom one, so it's going to be n minus 1. And then we're going to add it with the last term. All right, so we're going to add both the second last term and the last term, and you're going to see why in a sec. So what does this do? Well, if we subtract these two sides, AB doesn't get canceled with anything. But if you notice, all of the anything with the A as a coefficient is going to get canceled. Because if we distribute BR into this, we're going to get ABR minus ABR, which get canceled. And all we're going to be left with is DBR. Here, ABR squared and ABR squared get canceled off. And we're going to have 2DBR squared plus DBR squared, which is going to leave us with DBR squared. Because we're going to this 2DBR squared minus DBR squared. And if we continue along, we will have A plus 3DBR cubed minus A plus 2DBR cubed. So we're going to be A, let's write that out, A plus 3DBR cubed minus A plus 2DBR cubed, right? Because we multiplied in R. Now, these two are going to cancel out, and this is going to be left with DBR cubed. And you can see that this is going to continue as a pattern. This is going to be extending all the way out to this. We're going to be left with dBr power n to the power of n minus 1. And then we're going to subtract off this last term, a plus n minus 1d br power n. All right, now, what exactly are we going to do with this? Well, this is essentially just going to be t1 plus tn. We're going to keep that. And this right here in the middle is going to be its own geometric progression. Let's factorize dBr out first, because this is going to be equal to 1 plus, factorize dBr out, we get r squared, all the way down to, we're left with rn minus 2. Right, so this is going to be equal to an actual progression here. So if I am correct, let me just double check my notes to make sure I'm not screwing this up here. All right, yep. I'm not, okay, yep, I'm not screwing this up yet. All right. So we're going to have t1 plus tn as usual. We're going to expand this out later because working purposes, but I'm just going to keep it simplified. dBr times, now this is a sum of a geometric series. Now we can actually use the formula that we used above for the geometric one. Let's recall, let me just rewrite it. The sum of n, recall, is equal to a times 1 minus r power n, 1 minus r, where n is the number of terms. Well, here we're going from r power 0 to r power n minus 2, so we actually have n minus 1 terms here. So this is actually going to be equal to Sn minus 1. So this is going to be equal to, a here is 1, right, for a's first term, times 1 minus r to the power of how many terms are we summing? We're summing n minus 1 of them, over 1 minus r. All right? So in fact, this is equal to, let's write out what t1 is. ab plus a plus n minus 1 d r power n, br power n, sorry, plus dbr times 1 minus r to the power n minus 1 over 1 minus r. Okay? And in fact, this right here is going to be equal to, oh my god, this is going to be so long. This, all of this, by the way, is equal to 1 minus r. Remember, times Sn, because remember what the left-hand side is. So if we divide all of this over, we're going to get S of n is equal to ab times 1 minus, divided by 1 minus r, plus this entire thing over 1 minus r plus dbr times this over 1 minus r squared, because it's 2 terms. So this is the sum of n terms of an arithmetico-geometric, which looks absolutely hideous, I know. But, you know, this is what you get when you have a very complicated looking progression. So, wait, is that a, oh wait, it's not a plus, it's a minus, sorry. It's minus, oh wait, all of these are minuses, oops. So it's t1 minus tn, I forgot to subtract, so this is subtract. Now, let's talk about a certain thing. How do we find the sum to infinity? Or does the sum to infinity even exist? Well, the answer is yes, it actually does exist. Now, I'm not going to explain why this is the case, but in general, this right here is going to go to 0, because as n goes to infinity, again, and by the way, this works for the same thing. The conditions are exactly the same because we have a geometric progression that's embedded into this progression. So therefore, it's going to have the same conditions as a geometric progression. So r here is going to be, the condition here is that mod r must be less than 1. Therefore, if this condition holds, r power n goes to 0 as n goes to infinity, right? So what happens is we have this term here to worry about. What happens to this term when n goes to infinity? Because this goes to infinity, but this goes to 0. Now, I'm not going to explain too much. I'm not going to explain too much about what happens to this term right here. Yeah, I'm not going to explain too much about what happens to this term, but safe to say, this entire term will go to 0. All right, I'm not going to explain why it's 0 times infinity. This whole thing will go to 0. It's basically like sum. It's something to do with limits. Basically, this is going to grow faster. This is going to go faster to 0 than this goes to infinity. So therefore, overall, it's going to go to 0. So the S infinity of an arithmetic or geometric progression, this term, as I stated, this will go to 0. This goes to infinity. Overall, because this goes to 0 faster than this goes to infinity, this whole term is actually going to go to 0. Right? It has something to do with what we call like the growth rate of functions, where this one is going to grow to 0 faster, they shrink to 0 faster than this grows to infinity, because this is linear and this is exponential. So this whole thing goes to 0, and we're going to subtract off. This term is also going to go to 0, because r to the power n minus 1 is going to go to 0. R to the power n is going to go to 0, so r to the power n minus 1 will naturally, because this is equal to r power n over r power n, this is a constant, so this goes to 0. 0 over r is 0. Right? Well, okay, this is assuming that if r is 0, if r is 0, then we have, I guess, a few issues to worry about. But if r is equal to 0, we're not going to use this formula necessarily, so we can kind of neglect that for now. But safe to say, because if r is 0, then this whole term just becomes 0. But assuming that r isn't 0, right? Assuming r isn't 0, then this becomes 0. So we're left with dbr times 1 minus 0, which is 1, over 1 minus r squared. So this is actually the sum to infinity formula, which is much simpler, right? Because you notice if r is equal to 0, this whole thing just goes to 0. This whole thing just goes to 0, because if r is 0, we don't even need to care about what happens to this one. It just goes to 0. So this is the sum to infinity formula of an arithmetico-geometric progression with starting terms a and b and common ratio r and common difference d. This is like the culmination of everything we've learned, and is a very messy thing. It's not really taught anymore, aside from a few countries, I believe. But yeah, a cool thing to note. Yeah, this AGP. So an example of an AGP, before we end off this video, is something like 1 over 2, 2 over 4, 3 over 8, 4 over 16, 5 over 32, and so on. You notice that we have two progressions going on. We have an arithmetic progression starting from 1 and increasing by 1 in each term. And then we have a geometric progression starting at a half and getting multiplied by 1/2 each term as we go on. Right? So this is an example of an arithmetico-geometric progression, because we have an arithmetic here and we have a geometric here. All right, so that's an example of an arithmetico-geometric progression, and this one in fact does have an infinite sum because this condition is met. This one is mod r is less than 1, and this r is equal to a half, which is less than 1. So this one does in fact have a sum to infinity. I'm going to leave it up to you as an exercise to compute what that actual sum to infinity is. But anyways, that is the end for this already pretty dragged out long video. Hopefully you guys enjoyed it. Hopefully you learned something about progressions. And that's the end of this two-part series. Let me know if there are any other topics you would like me to cover in this sort of like long form uncut videos. And yeah, that's all I have to say, and I'll see you guys next time.